Hello, so today we are doing this problem called 0, 1 matrix. It's a medium problem on Leetcode, and the problem says we get a matrix of 0 and 1 and we want to find the distance of the nearest 0 for each cell. Basically the distance for each value 1 to the nearest 0, and basically an adjacent cell or move to an adjacent cell counts as value 1. And the adjacent cell are only the 4 directions: up, down, left, and right. And so, for example, we have this matrix here where for example, the zeros of course stay 0 because they are already at value 0, and the value 1s just takes the distance to the nearest 0 to it. So here the nearest is this one, or this one. We can do whichever direction, and all of them are 1, so we put 1. And for this here, the zeros stay the same. The distance for this one to the nearest 0 is just 1, and the distance for this one to the nearest 0, which is above it, is just 1, and the distance for this one to the nearest 0 above it is just 1 too. And for this one, the distance to the nearest 0 is 2. Either going up, it needs to go 2 steps, or going this way, left, right, then up, or going left and up, that's also distance is 2. And so we put 2 here. So that's the idea. Now how can we solve the problem? So the first thing we can think of actually is just a brute force solution. So how does the brute force solution look like? So what we can do is just go through the entire matrix, so like this. So go brute force solution first. Let's just take the example here. So we have these 2 examples. So this one is the first example, and then we have the second example. Okay. And so the brute force solution would mean just we go through the matrix. So let's say for I in range of rows, and then for G in range of columns, of course, and then we check if the cell at ij position is equal to 1. Then we do another loop on the entire matrix to find the one that is closest to it, and so that would mean doing the same 2 loops here, and then doing just KL, and looking for the cells that are equal to 0, and then counting the distance. And so we check if cell at KL is equal to 0, then that's possibly one of the nearest zeros to it. And so if that, we need to initialize some distance here, right? So by default we can just set it to infinity, right? So that what we find is using the min is always better. And so we do min. We set the distance of ij, of course, because here we would have, or actually let's just modify. We can also just modify the matrix, and so we can just say the value of ij is going to be just the min of the distance we obtained so far, and the distance between ij and kl. That's the distance between 1 and this 0, right? And the way we can obtain that is just by doing the absolute value of the difference between the x coordinates and the absolute values between the difference of the y coordinates. So that means I minus k plus absolute value of j minus l. And at the end we can just return our a. But this solution you can see here, this is in the, if we say that the matrix like R is the length of A, and then C is the length of A0, then that means here this is O of R, and this is O of C. And so the overall here so far is O of R by C. And here it's also O of R, right? Because we are going through all rows. And here it's also O of C because we are going through all the columns. And so the entire thing is, it's O of R multiplied by C 2 times, right? So squared. And so you can see this is really not good because it's the size of the matrix quadratic to the size of the matrix, so that's not good. So we need to immediately think about a better solution. No need to code it up because certainly if we code it, we will get a time limit exceeded exception here on Leetcode. And so another way we can solve this problem is, the problem says the distance to find the distance to the nearest zero in each cell. And so if we think about this a little bit, a distance to the nearest zero, that means we are looking for a shortest distance, right? And whenever a problem asks us for the shortest distance, that means we are looking for our shortest path, right? Shortest path. Whenever the problem asks us for shortest path in something where we can find neighbors, like here we can find neighbors using the directions up, down, left, and right. That means that we can use BFS, right? So that means we need to think right away about using BFS. And so the way we can do BFS here is that for each cell with value 1, use BFS to find the 0 closest to it. And that's pretty much it. And so then we can do that right away right now. So we need to go through the matrix to find cells at value 1. And so that means we need to do something like this. And for G in range of length of A0. And we need to check if the value at is 1, we need to do BFS, and we need to replace the value of J with the result of BFS, right? So we want to do BFS on IJ, and then we need to define our BFS. And so right now that we have that, let's do our BFS. So we need a queue, which is collections.dq on something, and then we need to keep track of distances so that we can know if we find a better solution or not. And so we need to just do something like this with default dict. So what this means here, passing this here, means that if the value doesn't exist in the distance, it will just make it default to infinity. And why do I want this? I want this infinity the same way I used it here, so that the first distance I find, that will be considered better than infinity, and it would be assigned. And then after that, if we do another pass and find a better distance than that, let's say better distance than, let's say first we find a 0 that has distance 4. If we do another pass, we will find one that has distance 3. We want the distance to be updated, and so this is why we are doing this. And now let's continue doing our BFS. And so we need to add something to our BFS here, which is we need to fill it up with the start position, which is IJ, and the distance starts out to be 0, right? And after that, we need to go through the queue and do BFS template. And so we need to pop the first element, and so that would mean doing this, and that would give us whatever node we put, so the position and the distance. And then we need to go through the neighbors. And so let's say nj and the distance for the neighbor. I'm just going to write the function here. I will write the definition later, but I suppose that I have this function that will return me the neighbors of ij and their distance, which is just this distance plus 1. And so like this. So we'll define this function later. So it will give me a generator of neighbors that I can just use. I could also just put it here, but it's just easier to read, to putting it in another function. So, and then we need to check if we have a better distance. So if we have a, how do we check that? So we can just check if the new distance that we have, which is dn, is better than the distance that we had before on this position. And so we check if it's better. So this is a map. So if it's better because it's smaller, then we need to assign it. Then we need to put that value for it here. And also, if it's better, then potentially, let's say this is 2 and the distance used to be 4. So maybe there is another value 1 that is just, maybe there is another value that is better, that is just after this dn. And so we need to put it to the queue so that we can add it to the queue so that we can get a result from that. And so we can just say nij. And we need to add the distance. Because this is less, it's potentially we might find a better path for the others through it, and so we need to put it in the queue. And then once we do that, we need, so BFS, what it does here for the shortest path is find the shortest path from source to destination, right? So BFS shortest path is from source to destination. And we know our source is the cell with value 1, right? So what is our destination? Our destination is the first 0 encountered, right? Because that would be the nearest one we are looking for. And so that means we just need to check for that here. This is the template for BFS for finding the shortest path. It is after popping the value off, we need to check if we found our destination. So did we reach our destination? Our shortest path destination. And we check that by checking if this is equal to 0. That means yes. And so in that case, we need to just return the distance. And otherwise, we can just return the value at ij. If we never find a 0, we can just return the value. It may be just to 0 itself. And that should be it for this one. Now let's implement this neighbors, finding the neighbors. So neighbors are in, so we need the directions, and so those are going up, going down, going up, and then going left, right, sorry, and then going left, and then calculating the positions using that. And so the position would be I plus n dx and j plus dy, and then the new distance for the neighbor is just the distance for d plus 1, right? The distance d plus 1, because this is just one more step, right? And then we need to check that it's in the boundaries, right? That's what we usually do. So we check if it's valid, and we need that's pretty much it. And then what we do here to feed it to this for loop, we can in Python we can use this thing called yield that will just keep calculating, and whenever it finds a value, it will just give it to the for loop here. And so something like this. And so this is useful because it lets our BFS code be more clear, because it's not polluted with these checks that are not really the core part of the BFS code here. And that's pretty much it. And so at the end we need to return A. Okay, so let's see here. We did BFS for each cell at value 1, and we put the value in A, in the position ij, and then with our BFS we found the best distance, and when we reached 0 we stopped. And that's pretty much it. So let's run it. So it's called matrix. Let's rename that to A here. So we should put this in quotes. Okay, that looks good. Let's try with the second example. Okay, so it seems like it passes, so that's good. Now, so let's think about this for a moment. So for this one, this is O of R and this is O of C, right? So over O of R, C. And BFS is usually O of E plus V, right? And so the number of edges here in our case are RC plus RC, right? So it's still too big actually, because this is still 2R squared for the BFS, and then we have the complexity of the for loop above it, and so it's kind of still too big, right? Because we have still R squared. It's a little bit better than the brute force, because not every cell gets examined in the BFS, and we stop early here, but it still can go up pretty high, right? And so why is that? The problem is that we are running a BFS for each cell with value 1. So what we can do instead is, what we are looking for is, it is possible to run BFS on multiple sources. So start with multiple sources and reach multiple destinations. That's definitely possible. And so what do we want here then? So we want to start our BFS on, so we can reverse this. Instead of starting from ones, start BFS from all zero value cells, and find the nearest ones to them, right? 1 cells to them. Basically, this idea is valid because a path from X to Y is the shortest path. If we find the shortest path from X to Y, that's equivalent also to finding the shortest path from Y to X. And so if we find the shortest path from 0 to 1, that's the same as finding a shortest path from 1 to 0. So what we'll be doing here is finding a shortest path from any 0 to any 1, and with that we can do only one BFS that fills the queue with start with all cells with value zeros, and then just updates the one and update the ones it encounters, right? Update all the ones it encounters. And so that would mean we no longer have multiple BFS. We will have just one BFS, which will significantly reduce the runtime, because at that point we will be able to just do this to collect all the zero values. So collecting zero values would be this. Then after that we will do BFS plus BFS. So it's plus, it's not like nested. So then we will do BFS, only one BFS, so that would be O of E plus B, which would be, in our case, it would be O 2R multiplied by C, so approximately still this. And so at the end we will have R plus R multiplied by C, which is a lot better than RC squared. It's just this, so it's a lot better. And so let's code this solution up then. So we'll still need the valid neighbors. We'll still need to do BFS, but differently. So let's run. And so we need to put the 0 values, right? So that means instead of doing this, we need to check for 0, and we are not going to do BFS, we are going to do something different. And so we need the queue, which is a collections.dq. And it's not starting with one value, it's multiple sources from all zeros. So we need to add to the queue all 0 values. So append ij, and else we are going to just put in our for values of 1, we are just going to put infinity, so that whichever distance we find is always better. The same thing we did with this here, where we initialize it with infinity first, so that we can find the better distances. We'll be doing that here. And so this is the O of R by C part, the collecting 0 values part. Now let's do the BFS part. Now we will just need to do while q, the normal BFS thing, and then we will need to do pop the front of the queue, which would give us ij, and then we will go through the neighbors, right? So that would mean in valid neighbors for ij, and at this point I'm not using distance, so I can remove it. And so here we need to check if it's a better distance, but since we are storing the distance in A already using this, I'm not using the extra distance distance array. Now I can just check if the new distance is, if the old distance that was at the position n, I, and j, if it's worse than the new distance, which is A of ij plus 1, which means this distance, new distance, is better, then I can just put the new distance, right? So that would mean will become this, and then we can add to the queue this new position, because it may lead to better distances for the other ones, right? And then at the end we can return just the value A, because we would have updated all of them. And that's pretty much it. So the benefit of this is that it will go through anything that is a 1 and update it. Because if the value is 0, then this condition will never be true, so we will not enter. But if the value is 1, we would have set it to infinity, and this condition will be true, and we will enter here, and we will put a new distance, and then we'll keep doing that for all zeros until either we find a new distance that is better, or we don't, but we'd have already updated. As long as there was a 0 in this queue, all the ones values will be updated. So yeah, I hope this is clear. So let's run it. Okay, so it seems to be working for that example. Now let's try the other one. Yeah, the way I pasted the code is a little bit. Okay, cool. Let's submit. Okay, so it looks like it passes. You can see it's better than the previous one in terms of time. So basically the previous one had this time and this one is a lot better. So another way to make this even better is, you can see here what I'm doing is that I keep trying to find a better solution. I said usually BFS is source and then stops at a destination, but I'm not checking any destination here. I'm just updating, keep. So with the matrix maybe too large, it will still work, but I'm still doing a lot of useless checks here. And so how can we avoid that? We can change this a little bit and make this make it better. And so another thing I think would be make it easier to see is if I have a separate distance list. And so let's have a separate distance list that starts out as 0 for all of them. And so this would be for this in range of length of A. And we'll still need to fill these values like this. But we no longer use this, and I'm going to use the thing I used before, keep track of the distance, so that I can check here if I reached something, so I can check here and put the distance, update the distance value. And so to do that, I'm just going to start out with 0 because we are already at a 0 value. And then here I'm going to update distance of ij to be equal to d. And we need to have a visited set so that we can prevent from visiting a lot that we were doing before. And so the way we are going to do that is by doing just keeping track of x. So basically visited is going to be all those that we added to the queue. So first we know we visited these because we added them to the queue. And so one other thing I want to do is separate these coordinates so that it's easier. So this would be something like this. And this is in the range of in queue, right? And now I have the visited set, and I can check if this is not in visited set, then I do visited, right? Then I append it. But if it was, then I skip it. So this would avoid some duplication, and here the new distance is d plus 1. Okay, cool. And we need to add it also to the visited set, right? When we visit it and add it to the queue, we need to add it to the visited set, so that would mean add an I and j. And we are updating the distance here, and then we need to return the distance. So this way we limit the number of passes that we need to do compared to the previous solution. Okay. Okay, so distance here needs to be, yep, so I said it's 0 values and I want to return it as a matrix like this. So actually what I should do is this. It's not a map, it's okay. Let's test with this one. Okay, so that passes, and hopefully it gives you another way of implementing this. So now we are just putting in visited and using the fact that with DFS, the first one that it reaches from any of these zeros would be the best distance. Yeah, so this one has this complexity of RC because of what we said here. We are first collecting the zero values, which takes us of R by C, and then doing BFS separately after that, using using O of R by C, right? So whenever we have something nested like this, it's always a good idea to think, okay, how can I make these two loops not run nested and run them possibly in separately, so that I can use some extra space and put some pre-processed data using the first two loops, and then use that data to do the second two loops, which is what we are doing here with the help of BFS. And yeah, that's pretty much it for this problem. See you next time. Bye.